Hello students, welcome to EPG Pathshala. I am Indira Ghosh from JNU. Today we are going to talk on module QSAR and data driven predictions and especially 3D QSR and under the paper computational biology. Yes, today's topics is to talk about the three-dimensional descriptors and what role they play in quantitative structure activity relationship. What are the 3D descriptors, why it is used, and how to build model using 3D descriptors. Their interpretation also will be discussed. Then I will go to the module is data-driven research on chemical structures and activity relationship. Why you use 3D descriptors? Same case study like QSR. Only thing is that though not the target structure may not be known, however, we try to find the chemical structure descriptor which is related to the chemical structure, ligand chemistry and ligand surface and three-dimensional structure. So 3D QSR differ from 1D QSR or 2D QSR by using 3D structure of the ligands, though the target where they bind is not known. I describe here the descriptors in 3D QSR method. As you know very well that QSR, standard QSR can take care of very different kind of molecular, electronic and even atom-wise properties and develop the biological interaction and regressions. 3D QSR on the other hand actually dealt with the continuous force field or surrounding the each chemicals as how it will interact with the receptor. That means it gives more than just an atom-wise or molecule-wise effect. It tries to give you how the complementary field of receptor would behave to it. Hence, exclusive receptor site, if it's not known, some of the compounds which inhibits those, this is the ideal method to use. So, what are these descriptors? These descriptors are nothing but potential interaction energy or force fields, which I will describe in appropriate module followed. However, this on the average, it is about the small molecules or ligand or the small chemicals which are going to bind to a receptor. The interaction field of such small molecules. It will be included sterics, electrostatic, in some cases even hydrogen bond interactions also are included. Also, as because it is a potential energy field, instead of taking the contour-wise contribution, sometimes I will show you that also is taken care of. Normally, it is taken by grid-based collection of point values. So, any method we use here, it is mostly a discrete value. Sometimes it might be very small values of discrete values. However, this requires that all of the molecules for which we are going to calculate the descriptor must be aligned appropriately and then the descriptors are calculated. In 3D QSR, the parameters, as I have said, these descriptors are called structural descriptors. And very obvious reason, structural descriptors are of very importance in doing the QSR. Now, the most common structural descriptors are like pharmacophores or something like molecular fields, which will be shown you. However, as I mentioned, even in previous slide, superimposition before calculating such field is a must, so that in the same frame of references, the values are calculated. However, when one designed for regression, one needs to convert this data into 1D or a set of numbers after all. So, we must understand the underlying assumption for such a method. And here I summarize most of them. One is, it has an effect, it produces what is the compound itself is binding to the receptor, not its metabolite or fragment or something. As well, it should not have a different conformer for bioactive and different conformer as such. So we take one can take a minimized structure or one can take few different structure and calculate the fields. However, it is considered that that conformer actually is the bioactive. Similarly, it is expected for all the compounds for which the QSAR is to be generated, they must be binding to the same binding site. Also, it is explained that it is expected that most of this process is not driven by entropy. Rather, it should be driven by the enthalpic method. So, it is very important to note here that such an compound conditions we can have to have a equilibrium. So no kinetic aspect or something like pharmacokinetics, etc., those or solvent effect or diffusion effects, these are not considered at all possibly in this interaction. Basically, the 3D QSR assumes that it is like it is going to be seeing a complementary surface, singles one type, and how it will behave, how better it will behave if its own nature is modified. So please do note for sure that what are these fields. Now I will show you by this slide how to do the field calculation. This is nothing but at the grid, I said that put a grid across the active site, and each voxel you just calculate the forces between the interacting partner, which is receptor, which we don't know, and the target molecule, which is the chemical compound. Now, how we find it? We presume that the partner or the receptor should be either water or something like octanol or other solvents. That means if it's a water, it will be more like ionic liquid. If it's octanol or other solvents, it's like a lipid. So, interactions are measured by finding the interaction energy between this type of interactions, which mimics the protein or mimics the lipids. I would describe to you what are the well-known molecular fields in this 3D. One is molecular electrostatic potential, which uses unit positive charge probe and finds both sides energies for every chemical surfaced with a grid. Now, another method is molecular lipophilic potential. There is no probe necessary. This is actually a volume representation. So, that can also be converted into a 3D molecular field. Of course, the grid is another where it includes, the program grid actually includes steric, hydrogen bonding, electrostatics, everything if necessary. Hence, most preferably, one uses grid potentials for all these calculations. Another is a COMFA, which also uses more or less like grid potentials. In addition, it uses some kind of indicator, parabolic. Sometimes also when I will depict more of COMFA so that it will be clear to you what more level they use. Started with Kramer's group. It was embedded in Tripos software. To tell someone more additional statement here would be worthwhile. Tripos, softwares, etc. are no longer existing probably. However, the concept or the science behind this concept of 3D QSR came out by the Kramer, and it is so well known that people actually use even today 3D QSR associated with COMFA. It's very interesting because it's called comparative molecular field analysis. Now, what is that comparative? Comparative means between different interactive field of different chemicals, we find out the difference between each one of them. And that's how you want to extract the 3D descriptors. And then we fit an equation. And then it becomes exactly like another QSAR method and follows all the rules and rigorousness of QSAR method. However, this has lot of advantage which I'll talk later on. This slide describes a grid with energy field, how it is calculated. So you have to put the grid inside. Then you must calculate all these electrostatic interactions which is embedded into the formula. Then one uses sp3 carbon atom. Why? That is to show the volume of the grid. And actually that carbon allows it to have the steric as well electrostatic, because charges is put as +1. Hence one can find both the fields, how it is will react to the any receptor which is not known here. Here I am showing you a picture of COMFA, and when it is done with a grid. This is a molecular fields. Now if you look at the colors coding, you can see from all the 4 pictures how they are depicted. So volume is encapsulated by using the small grid in grains. Each of these grid values will be extracted and used in COMFA calculations. Hence, then there is a small linkage between this blue color and green colors. They depict different type of electrostatics and hydrophobic and hydrophilic forces. As you notice here, this picture gives you clear idea that they are not to be, in a chemistry, they are not necessarily to be continuous. So, next we'll show you how we utilize these values or grid values and extract them to build a model. How one corresponds to 2 types of variable in QSAR. Now, most often these 2 types of variables are steric and electrostatic. They can be more than that, that is, they can be hydrogen bonding functions as well, but they can be taken as the technique of PLS, which is partial least square technique, which is applied to have compute the coefficient. Now, as you notice here, if we follow the proper procedures even of calculating these grids, one most important factor is that must have a superposition of the molecules which should be optimally aligned. Otherwise, the different kind of chemicals, different kind of grid field would look at a different way. Now, if we look at the molecules inhibitors, they must be superimposed with their pose, how they are putting themselves across the receptor. And this sometimes becomes very difficult. However, having a different orientation may change the QSAR model as well. These problems hardly been handled, as well as the flexibility of the molecule. Now, this problem comes when you have a inhibitor which is too much flexible, like peptides, which are generically very, very flexible. So doing a peptide and COMFA, people have attempted, which has becomes very difficult as such. One needs to know what orientation or what posing all the peptides would bind to a expected receptor. Repeatedly, I must mention to you all the time that we do not know the receptor, and that's where COMFA becomes some kind of a predictor for what could be the receptor as well. Here I show you a CYP450 CAM with camphor, a predictive map. Now, taking the compounds and building up the map, it looks like here. Here I show exactly. So blue is the positive charge contribution. That means the interaction site which shows blue is very much to interact with a positive charge. Red is the negative charge representation. Similarly, green is the area which is sterically not available, and yellow is a conflicting area. That means it can have the green as well as the red. This type of difference also can be found out from COMFA. Hence, substituting, if you take different substitutes at those positions, one can actually find out what could be the picture of a receptor. Another software which gives very clear picture and also available even now, even without having COMFA, one can use these, and developed by the academic groups, and many people have used Vexarf more rigorously than COMFA, and this program has been used for mostly to do ADME properties, which I have said, and build many pre-calculated ADME property. And this model includes more than earlier. That is, it can predict very well drug solubility. It can predict some kind of absorption, which is very rigorous and very important for most of the drug designing. Also, it gives good predictability of blood-brain barrier permeation, and it also gives distribution in cell. One have to look at how the Vexarf works. Actually, Vexarf reads or computes the same molecular fields It uses grid at its burner, that is important serving by grid. Every descriptors are calculated. Descriptors are all characterized with respect to size, shape, polarity, hydrophobicity, and even how they ratio of them. And I will show you in next slide the values actually how they are. Size, shape, volume. Now how it is, not only it considers volume, size and shapes, ratio of the volume to the surface is also used. Globularity also is used. So you can see that's the reason it gives much better predictability for ADME properties. Then it gives hydrophilic surface, but it also gives the capacity factor. That means how much is the surface are actually hydrophilic or hydro exposed. Also it gives similar factor like hydrophobic also. So it not only gives a hydrophobic, also it gives like a hydrophobic, just like the hydrophilic area. It also gives all the moments. Not only gives the energy, it actually gives the moments. So what it defines as integer moments, which is in a figure I have later described to you. But basically the moments gives a lot more information than only the energy. And many of the local energy minima, many of these distances and other like packing parameters, polarizability is included in Vexarf descriptors. So how it works? It's regular QSAR. Only thing one has to do is convert them into proper descriptor, which is done by these softwares. And then you use PLS or PCM. Why PCM? The reason is many descriptors are deserved, and here I can show you in figures how many it can grow. However, the number of compounds may not be so many. In those cases, we must reduce this number of compounds, keeping in mind the earlier QSAR best practices. So you can have 72 descriptors maximally in such a method, and there are 5 classes. Some belong to size and shape, some belong to hydrophilic, some belong to hydrophobic, also the integer moments. Now, as I said, these are the models which have been already predicted. Slide shows you how we come up with that number. So the numbers comes like, hydrophilic region descriptors would be something like 30 descriptors. How you get? Like you can have 8 of them. What are these 8s? 8 are volume of interaction with water probe at 8 energy levels. So we can devise our system or every inhibitor to have such a molecule. And then we can calculate and we can find out all the kilocalorie per mole. Then we can have something like 8 moments for proportional to the distance between the center of mass and the center of hydrophilic region. So that can be also, because that will be 8 energy levels. Similar functions as I've shown here will be included. The descriptors visualization here. This is the benefit what you get when you do 3D QSAR. So how to find hydrophilic 8 are shown here, and 8 the 8 integer moments, that is very clearly shown how the structures are shown here. So interaction volumes are shown here on the left hand side pictures with -4 kilocalorie per mole energies, and the moments are shown by arrows. You can see the 4 arrows over there, and on the right hand side, which is corresponding to -1 kilocalorie. That's why it is pervasive, almost covering all part of the small molecule. But there are 4 moments there too. Hence, you can calculate these integer moments or integer moments at the 8 values. So one is -4 kilocalorie molecule or -1 kilocalorie molecule. So one must understand that we can actually calculate as many like these functions as illustrated here. So as we have discussed, Vexarf, here I represent a Vexarf area. Vexarf software actually shows you this volume. You can see on the green, on the green molecule is shown on the green color, the chemical structures of the molecule, and Vexarf actually is building a effect or complementary surface which is shown blue color as a hydrophobic surface. And this is not at all to relate to anything to do with target. So no target coordinate, but it can depict what would be the volume surface or surface area and color it by different and type of coloring. Depend on blue is hydrophobic and hydrophilic is red color. One molecule, which is the ligand, can be shown here. Here I compare the summary between ADME and QSAR. That is, the ADME and QSAR field, the 3D QSAR, there are several different level of QSAR. 3D as well as standard QSAR. Now, there are software called MOE by CCG groups and very good and predictive models they give, but only binary QSAR they used. Also, they do not have many modules for ADME, which they have recently developed newer ones. Swedinger has basically no 3D QSAR earlier, but they had a lot of new model, and they also consist of quick prop, which is ADME prediction, and they have some phase called program, which is looks after the pharmacophore types. Auxiliaries or BioVia, which is newly companies, but Auxiliaries is the older company, who also have many traditional QSR, but doesn't have much of 3D QSR. Also, not many ADME module was there. However, recent ones, more versions are having the more address towards the ADME. As I have mentioned in the lower, that is, last 10 years, many players are looking at ADME, and this has become more competitive area for the matter of our research. Here I compare simply with that few models, and this comparison is rather qualitative, hence can be taken with a pinch of salt in that way. Now, QSR and with a COMFA, that generates not only predictive model, but it's a very interpretable predictive model. Also, we must understand that it's a very many generalized and very different techniques have been used for it. Now, most importantly, this kind of prediction, that is 3D COMFA or 3D QSAR, it not only gives a picture of the module and QSAR, it also gives us a good interpretation, a very well concept of what could be the receptor actually, because it actually shows the receptor surface complementary. That is complementary receptor surface. Now, HQSR on the other hand, it's a very fast and quick system, used to be in Tripos software and Distill as well, but there is no alignment necessary, and it is part by part or fragment wise QSR is done. Distill is another which fragment wise clustering is done. Vexarf is rather addresses very, very well established and significant, and consistency of QSR model is highest in Vexarf, and which addresses ADME problems. Hence, many pre-built model also has been included in this. But this contains all the references. Especially, it starts with Cruzini, who has Vexarf developer and predictor, and programs can be available from him. Kramer is owner of COMFA and others. However, I have taken a liberty to put few more people's name like Ekins et al. And DeVos et al. Etc., who have contributed quite a lot using 3D COMFA in different, or 3D QSR, sometimes Vexarf, sometimes COMFA, to predict and build good, well established model in case of predictivity of cytochrome 450, which is used for metabolite predictions. Also, sometimes in different aspect of excretions. So I'm going to introduce you another concept, and which is called data-driven predictions. In this field of ADME, which is will be detailed in next few slides, which are not just biological binding efficiency to the target. However, most often it is not known which targets the ADME binds. That is, during this activity, which is more of a physiological activity inside the cells, which are the targets they bind. But many common properties of the drug or drug-like molecules can be utilized and predict what could be the real range of values of these predictors. So this is a case which is little different from QSAR. However, it is a data-driven predictions which I will describe in few slides. Well, I would like to bring to your attention on new topics, and that is, as I described earlier, everything in data-driven systems can do a lot of things, and very simple rules can be developed where you do not need to go through a lot of regression which I have described earlier in QSAR and 3D QSAR. However, the predictability is a bit of a question mark because it may not be uniform all the time. Now, where we should use this database driven? Where we do not have enough information exclusively, like if we do not know single receptor binding case, like case of lead after lead to doing the optimization, we go through a many of pre-formulation things, and that's called drug development group. And after the drug discovery, one has to go through pharmacokinetics. That means it should have enough pharmacokinetics method, must be readily bioavailable. That means oral absorptions. One should also look at the structure activity relationship so that it is soluble, or it is not so soluble that it retains itself only in blood cell. So these balancing acts are done also by certain extent by QSR and enhances the likelihood of successful heat. However, the attempt in by Chris Lipinski was exorbitantly new idea, and I would like to emphasize that in my next slide. Biological activities can belong to bioactivities which we have discussed earlier, and major things have been discussed even more details. However, most often the ADMET or this efficacy, that is absorbance, drug metabolism, interaction, excretion, etc., and these are related to sometimes one or two receptors whose structures may or may not be known, are still the difficulty of building any QSAR. And this is where the rule which developed from drug database was a great useful. Professor Chris Lipinski in 1997 published a paper which is a seminal work and a very simple rule he derived, which will be discussed in the next slide. Here I am showing you the databases has been used by Chris Lipinski while exploring the dark space. He actually took a very much interesting databases, like he include drug database, he include which is shown by MDDR or pharmacopoeia, which has already been known as a drug. He also used new chemical entities. When the synthetic chemists design compounds, they also collect. So he used many of those. He even used reactants, which is given by acidic compounds. And then he used some of the set of compounds which are called fast alert composite. And these compounds actually contains which are not almost passed through the filters of going to the new chemical entity but failed in a later part, like toxicity, etc. Having collected this whole database gave him a real comprehensive database of yes, no, very well, everything, and built the model to predict what could be the range of certain descriptor properties. The rules which was valid and found to be amongst, considering all the databases have been shown in the previous slide, was found to be as follows. The molecular weight of the already well-known drugs which has been designed by chemists is always between 200 to 450. Almost 85% of the drug follows this. Then another 85%, same 85% of the drugs follows the C log P values between -1 to 4.5. Similar seen in the case of number of rotatable bonds. The drugs containing many rotatable bonds up to 9, at least 75% of the drug contained such characteristics, and maximum 5 rings, maximum, not at least, maximum 5 rings contained in 90% structure. So rings, rotatable bonds, certain range of value of C log P, molecular weight were found to be existing amongst all these drugs. When it was analyzed related to hydrogen bond donors, it was found up to 5 hydrogen bond donors available for 90% of the drugs. And it was found up to from 1 to 8 hydrogen bond acceptors are available amongst the 80% of the molecule. Hence, following these rules or observation, a great idea came out from Chris Lipinski, and he developed a new rule called Rule of 5, and that is very simple chemist, and these are just derived from database rules, so that very simple screen out of ligands with potential permeability problem can be translated to the poor permeability mostly. However, to note that these rules only to exclude compounds which belongs to not follow these rules are chemist synthesized and laboratory synthesized. Many compounds which is derived from natural product may not have such follow-up. However, let me rephrase the whole rule of 5 is any compounds which violates this most likely will not be a good permeable and ADME factors. What it rules are: molecular weight should not grow more than 500 Dalton, C log P must not be much more than 5, hydrogen bond donors should not be more than 5, hydrogen bond acceptor should not grow more than 10, and rotatable bond should not be greater than 10. The most interesting understanding here is it's not the regression or any mathematical formulation, but there is a very nice mechanistic view which takes care of each of these boundaries. And that is actually, it tells a lot which are the compounds which is highly soluble in water or in blood will never be available or accessible to the place of site of binding. And many cases, too much high log P would bar it to go more than deposition or maybe absorbed in the tissues only, will not be able to come out of it. Hence, it's very important that compounds which violates these rules are only contained in drug compounds are only 10 to 15%. And that is a very remarkable contribution by Chris Lipinski. However, this Lipinski's rule of 5 has been in different way manifested, and slide here shows summary of that, which tells you that publication is referred here, and that is the cutoffs. That's the cutoffs, and why the rule of publication this is. So it should be remembered that poor absorption or permeation are most likely because of if there are more than 5 hydrogen bond, if there are molecular weight is more than 500, if the C log P is more than 5, which shows that it includes poor dissolution solution, and sum of N plus O it should not be more than 10. Obviously, this is a limiting factors which has been described here in this slide. However, question comes, is the rule for a drug? But what about when we are designing a compounds to become drug? What should be our limiting factors? And slide talks about that. There is rule which has been suggested by Tudor and other groups, which says that lead library should be having cutoff between 150 to 400, C log P should be -1 to less than 4.5 and less. So these numbers are derived from known lead library as well as from a very good common sense, that is, while you modify the lead to become good permeability, good efficacy and good ADME property, one actually has to add up few groups. So there is a scope of addition of groups. Thinking that, as well as evaluating such rules in a well-known, already available companies' lead libraries, these rules have been formulated. So, it's a very interesting work which has been depicted here from the designing point of view. However, it's very simple, and collection of compounds gave us this direction. Most importantly, each of these factors which has been depicted here are very important descriptors whenever one develops a QSAR. This is a summary. In the first part, I have described you how to utilize 3D QSR, how to build the descriptors for 3D QSR, and where it is very much interesting. Basically, it includes the interactive mapping of or complementary surface of the compound. That means what are the factors which decides that the molecule is going to bind to the active site, and how to utilize them and efficiently build a model to predict. I also have used another technique which has been depicted and mostly used for drug metabolism and prediction of even toxicity or excretion rate, etc., which is driven by chemical data collection of drugs and associated chemicals, so that these criteria can be utilized also to build models or filter some of the chemicals to be utilized in the next phase, that is actually the most last phase of preclinical data management. Yes. Thank you.